Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Shalom Nama Budayun. In this video, I will explain again about metallurgy for the non-metallurgist. But first, I want to introduce myself. My name is Putra Hutabarat with student ID number 23055531075. I am from Mechanical Engineering Study Program from Engineering Fakulty from Udayana University. Okay, in this video I will explain about chapter 5, that is modern alloy production. Okay, let's start. Modern alloys are manufactured using various melting, casting, and fabrication techniques. The choice of manufacturing process depends on factors such as the alloy system, product system form, required condition, and desired properties. Most commercially available alloys are produced using melting and solidification techniques, including iron melting, vacuum melting, and powder production. After the liquid metal is produced, it is cast into molds to become an ingot or casting. More products undergo mechanical production operation to refine their properties, while casting alloys are used without further working. Okay, next. The next is point 5.1 effects of alloying on solidification. Solidification of pure metals. When a pure metal begins to melt, the solid liquid mixture stays at the melting point temperature until all of the solid has completely melted. Solid metals stay at the melting point until fully melted. The energy needed for the transformation is defined by the material's latent heat of fusion. For example, pure aluminum requires 398 kJ per kilogram to melt at 660 degrees Celsius. The temperature starts rising again only after complete melting. Next, conversely, pure metals give up their latent heat of fusion and solidify at a single temperature. If a pure metal is melted and allowed to solidify in the melting crucible, a thermocouple placed in the metal during solidification could trace a cooling curve like that shown in picture 5.1. The glazing sites from impurities promote solidification, leading to a different cooling curve at picture 5.1b. Solidification of alloys is more complex than pure metals due to different melting temperatures of alloy elements. Alloys have a music zone where solid and liquid coexist. The liquidus temperature marks the start of solidification, while the solidus temperature indicates completion. Different alloys have varying liquidus and solidus temperatures, shown as liquidus and solidus lines on H diagrams. Bridging a course from liquidus to solidus. Next, aluminium silicon alloys are another example of a major family of shape causing alloys with an eutectic point. The aluminum silicon eutectic is located at approximately 12.6 Wt% Si and 577 degrees Celsius on the binary phase diagram, picture 5.2. Alloys with wide freezing range can cause faults during casting, while those near eutectic melting point are advantageous for specific shapes. Aluminium silicon alloys are commonly used to cause engineering block in the automotive industry to reduce weight and improve fuel economy. The freezing range depends on the silicon concentration. Okay, next. Next is 5.2 solidification structures. Solidification typically exhibits planar, cellular or dendritic growth in the liquid depending on heat removal. Lung growth occurs with a positive temperature gradient, while cellular or dendritic growth occurs with a temperature inversion. Thermosparkling cellular growth occurs when the solid liquid interface becomes unstable, forming spikes that grow into cellular-like structure due to temperature difference in the liquid. Dendritic growth is a further manifestation of cellular growth in which the spikes develop side protrusions, this picture 5.4, at still higher undercooling and higher growth velocities. The cells grow into rapidly advancing projections, sometimes of complex geometry. Next. Dendrites are small crystalline needles shaped like penetrates, picture 5.6. So named after the Greek word dendros for the tree. Dendrites have a primary arm with secondary and tertiary arms that branch from it. The spacing of the secondary arms is proportional to the rate at which heat is removed from the casing during solidification. Constitutional sparkling. Dendrites form more in alloys due to constitutional sparkling caused by segregation of alloying elements ahead of the solid liquid formed. The concentration of these elements in the liquid reduces its temperature. Next, solidification zones. Metal cast into a mold can have 2 or 3 different zones or types of grain growth. A cool zone, a zone with columnar grains, and a central equation grain zone, picture 5.7. However, it should be noted that these 3 zones are not always the case. For example, a pure metal hardened structure has a cold zone and a columnar zone, but may not have an aqueous zone at the center. Next, tail zone. Nucleation first occurs on the interior surface of the mold because the mold is cooler than the metal. As a result of this temperature difference, the nucleation rate is initially high and the average grain size is typically small. Its nucleation events produce as an individual crystal or grain that grows dendritically in a direction roughly perpendicular to mold wall until it impedes on other grains. Picture 5.8. Columnar zone. Inside of the child zone, there are a series of columnar or column-shaped grains that are oriented almost parallel to the heat flow direction. Next, center equation zone. Equation zone at the center of some alloy castings has a smaller, randomly oriented grains with similar dimensions. Long dendrites may breed and serve as nuclei for new grains due to decreased thermal gradient or segregation during freezing. Low casting temperatures result in a fully solidified equation structure. Mesin freezing. Present modern metals with a narrow freezing range have mainly fiber structures, while frozen metals with a wide freezing range have similar grain structures. The formation of the first crystal results in a reduction in solid in the liquid and triggers the formation of the second crystal. This process repeats itself and produces similar grains in the solid material. Crystalline dendritic growth can be surfaced quite effectively. Non-dendritic solidification force. Semi-solid processing. Semi-solid processing produces non-dendritic solidification, allowing for easy flow and shaping of alloys. Next. Okay, 5.3 melting furnaces. Many furnace technologies are available for melting metals. For example, in steel making, where free iron is produced from iron ore, limestone, and coal. The aim is to reduce the silicon, manganese, and carbon content in the steel produced. Selection of a melting furnace depends on the specific alloy, casting operation, and production quantities required. Furnaces can vary in size with output ranging from a few pounds to several hundred tons. A fuel source such as propane or natural gas is usually used to achieve low temperatures. Meanwhile, for high temperatures such as steel alloys, the furnace is designed to reach temperatures above 1650 degrees Celsius. The temperature required for aluminum alloys falls between these extremes. Electric arc furnace. The furnace commonly used to melt steel alloys is the electric arc furnace, or EAF. It has a refractory line vessel with a bowl-shaped head covered by a retractable hemispherical roof. The roof may be refractory line of water-cooled. EAF uses alternating current and graphite electrodes to establish an electric arc and melting the scrap materials. The furnace is often put on a tilting platform for pouring the liquid steel into another vessel for transport. Next, induction furnace. Induction furnaces are widely used for melting alloys due to their excellent metallurgical control, low pollution, and high efficiency. They come in various sizes, are easy to operate, and can melt small quantities of materials quickly. They can melt a wide range of metals, but over-limit refining capabilities. Vacuum induction melting. Producing liquid metal through vacuum melting in an induction heated crucible originated in 19th century, brick thoughts in 20th century, developed for super alloys in 1950. These advances have had a decisive influence on the rapid increase of metal production by VAM. Flexibility due to small batch size, fast time of program for different types of steel and alloys, easy operation, low losses of alloying elements by oxidation, achievement of very close oppositional tolerance, precise temperature control, low level of environmental pollution from dust output, removal of industrial trace elements with high vapor pressures, removal of disulfide gases, for example, hydrogen and nitrogen. Next. The next is crucible furnace. Crucible furnace have historically been the most common type of furnace used, and records dating back to the dawn of the metals industry some 6,000 years ago indicate their usage. Crucible melting is a convenient process with flexible startup and shutdown. It allows easy alloy change and offers operation flexibility for foundries. Crucibles also have advantage over other types of furnace advantages include a small compact size and relatively lower acquisition cost makes them economical. Smaller and round furnaces provide and maintain good, even temporary profiles. Open crucible furnace, or even those with pivoting lid covers, allow easy access for ladling. Next, remolding. There are two commonly used remolding processes for metal refinement: electroslag remolding or ESR and vacuum arc remolding VAR. In both processes, an electrode is melted as it advances into the melting region of the furnace. As the working phase of the electrode is heated to the melting point, drops of liquid metal that fall from the electrode phase are collected in a lower crucible and rapidly solidify. The VAR process was the first commercial remolding process used for superalloys, and these furnaces can vary considerably in their size and capacity. An example of a representative 30 tons furnace is illustrated in figure 5.18. Other furnaces, several other types of furnaces have been developed for special applications. For example, the skull melting technique is used when melting highly reactive metals that would otherwise attack to the walls of a fireplace lined with standard refractory materials. Electron beam melting. Electron beam melting and casting includes melting, refining, and conversion processes for metals and alloys. In electron beam melting, the feedstock is melted by impinging it with high energy electrons. Plasma melting and heating. Plasma torches generate heat from an electrical current that passes through a partially ionized gas or plasma. The plasma is generated by the phenomenon known as gaseous discharge, whereby a gas is ignited by electrical breakdown. Next. And the next is 5.4 Molten metal processing. Fluxing of molten metal is often the first step in obtaining a clean melt. Fluxing is a term commonly used in the foundries and melting departments that refers to molten metal treatments from the addition of reactive chemical component or inert gases. The various functions of molten metal fluxing additives, either singly or in combination, include removing inclusions, impurities, or dissolved gases from the metal, preventing excessive formation of solid phase inclusions, preventing and or removing oxide buildup on furnace walls, injection or distributing alloying constituents. Molten metal fluxing agents may be chemically active solids, inert gases, or a chemical active gas. The type of flux depends, of course, on the composition of the metal and refractories in iron and steel making. For example, the function of fluxes is twofold: to render the high melting refractory oxide impurities fusible and separable from the molten metal. Next, to provide a medium with which the impurity elements or compounds would combine in preference to the metal. Next, fluxing is also commonly done to some extent with virtually or non-various mill and foundry melting operations. In particular, Fluxing is used extensively in controlling the rose formation and removing oxides from aluminum melts and melting furnaces. The basic types of aluminum fluxes are cover flux, designed to produce a barrier blanket on the surface of molten aluminum. Next, dosing fluxes with weighting action that promotes qualities of aluminum. Melt cleaning fluxes designed to remove aluminum oxides from the melt. Wall cleaning fluxes specifically designed for the softening and removal of excessive aluminum oxide buildup that occurs on melting furnace walls. Next, 5.5 Primary production casting. Static ingot casting. Several ingot casting processes have been designed and developed for the downstream manufacturing process. The fundamental requirements that must be satisfied by an ingot are the capacity to withstand subsequent mechanical reduction, operation without rupturing or cracking, with the capability to yield a commercial acceptable finished product. Next, in vertical continuous casting figure 5.20, molten metal is poured into the caster from the top. The temperature of metal is reduced as it passes through the water-cooled mold. Solidification starts from the middle of the mold, beginning at the outer surface of the mold and moving toward the middle of the embryonic ingot. In the manufacture of semi-continuous cast or DC aluminum alloys, the direct casting process is a method that is widely used today. This process involves casting aluminum into shallow water-cooled molds with the desired cross-sectional shape. Once the metal begins to solidify in the mold, the first bottom in the mold lowers in a controlled manner and water is sprayed onto the surface of the newly solidified metal. Almost all commercial aluminum ingots produced for further fabrication use the process. The DC casting process can produce ingots with fine grain size and little segregation with high production rates. This process can be done vertically or horizontally. Next, 5.6 Foundry casting. Foundries use different techniques to produce complex shaped parts with interior surface. Using mold made in various ways, the selection of molding metal depends on factors like part size, shape, quantity, tooling, and the molding metal used. Shape casting methods can be divided into three broad categories: casting with expandable molds such as sand, plaster, ceramic, and graphite molding; casting with erasable permanent molds; casting with erasable permanent molds with high pressure metal injection of the metal into the mold; die casting, sequence casting, and semi-solid processing. Casting with expandable molds provides tremendous freedom of design in terms of size, shape, and product quality. Expandable mold methods are classified further as either expandable molds with permanent patterns, expandable molds with expandable patterns. The patch power channel is also made in a disposable pattern. A common method is use patterns made from foam or wax. The use of expandable patterns increases the complexity and tolerance of the cast product. Unlike permanent patterns, for most expandable patterns are a positive replica on the part picture 5.24. In large form casting, for example, a A foam pattern is placed in a flask. Sand is then added to compacted around the foam pattern. During pouring of the molten metal, the foam evaporates and the metal solidifies in the resulting cavity. Permanent mold casting is particularly suitable for the high volume production of the casting with fairly uniform wall thickness and limited undercuts or intricate internal coring. Next, 5.7 Non-Ferrous casting alloys. Casting is crucial in producing titanium components, super alloys, and high-performance turbine blades. Investment casting introduced in the May 1916 and coupled with hot isotactic casing or HIT allowed for the widespread use of titanium casting. Ceramic slurry materials were developed to prevent reaction with the reactive modern titanium. Aluminum casting alloys. Aluminum casting alloys are the most versatile of all common foundry alloys and generally have the highest versatility ratings. As casting materials, aluminum alloys have these favorable characteristics: good fluidity for filling the sections, low liquidus temperatures relative to those required for many other metals, rapid heat transfer from the molten aluminum to the mold, providing shorter casting cycles. Hydrogen is the only gas with appreciable solubility in aluminum and its alloys, and hydrogen solubility in aluminum can be readily controlled by processing methods. Many aluminum alloys are relatively free from hot sort, cracking and tearing tendencies. Chemical stability, good as cast surface finish with loose through surface that silver, pure, no blemishes. Next, the most widely used aluminum copper silicon alloys contain both silicon and copper. The amounts of these two additives vary so that copper predominates in some alloys and silicon ion others. Copper provides strength to this alloy. Aluminum silicon alloys have eutectics that improve moldability and reduce sensitivity to high heat. Typically, alloys with a high silicon content are used for more complex molding and die casting processes, which require more careful casting techniques to avoid problems with alloys that are sensitive to high heat. Aluminum silicon alloys that do not contain copper additions are used when good castability and good corrosion resistance are needed. Alloys with less than the eutectic composition of the approximately 12.6% Si are referred to as hypotectic or hypo meaning less than, and those with over 12.6%. Alloys with silicon contents as low as 2% have been used for casting, but silicon content usually is between 5 and 13%. Next, magnesium casting alloys. Magnesium castings of all types have found use in many commercial applications, especially where their lightness and rigidity are major events, such as for chainsaw bodies, computer components, camera bodies, and certain portable tools and equipment. Magnesium alloys and castings are used extensively in aerospace. Next, zinc casting alloys. Die casting of over 90% of zinc casting tonnage. The commonly used zinc casting alloys are U and S, a Z3333520 alloy 3 and its modification U and S, Z33523 alloy 7 and alloys 5 U and S, Z35531 and 2, Z35541 are used for higher strength and hardness. Alloy 2, 3, 5 and 7 are exclusively used for pressure die casting. Next, 5.8 powder metallurgy. The general types of automation processes encompass a number of industrial and research methods. Industrial methods include fluid automation, where a liquid metal is broken up into droplets by impingement of high pressure jets of gas, water or oil. Yes. Centrifugal automation, where a liquid stream is dispersed into droplets by the centrifugal force of a rotating disk cup of electrode. This picture. Vacuum or solute gas automation, where a molten metal is supersaturated with a gas that causes automation of the metal in a vacuum. Ultrasonic automation, where a liquid metal film is agitated by ultrasonic vibration. Water automation. Water automation is the leading method for producing metal powders, particularly iron powder for press and sitter applications. It is also used for copper, nickel, stainless steel, and tool stainless powders, as well as thermal spray coating and dental amalgams. Next, gas atomization. The gas atomization process produces powder particles with a different geometry and surface chemistry than the water atomization process. Gas atomized powders are generally rounder and have a lower surface oxygen content. This process involves bringing molten metal by high velocity gas through a specially shaped nozzle. On a global scale, metal powder production with the inert gas atomization method is much less than with water atomization, around around 50,000 tons per year. The metal consumption rate is lower and the melt size is smaller. However, production of air atomized powders, mainly zinc and aluminum, as well as tin, lead, and copper alloys, is estimated at more than 300,000 tons per year. Most air atomizers can operate continuously for hours or even days. Multi-nozzle units are often used to increase production with aluminum and zinc powder. I think that's I can explain. If there are any errors in reading, please forgive me, and thank you for watching my video, and thank you.